Hi and welcome to this clip going through the Chemistry Olympiad 2007 paper, the sixth question. So this particular question has been selected because it is particularly good for first year A-level students because it covers oxidation states and molecular shapes. So these two topics come up early in the course, so this particular question is quite a good one to sort of get started having a go at some Chemistry Olympiad style thinking. And if you wanted to go and find all of the past papers and their mark schemes, you can go to the Royal Society of Chemistry's website on www.rsc.org/learn-chemistry. So on the front of every single Chemistry Olympiad paper, like you see here, you'll have a series of bullet points giving you some tips on what to do. So I'd like to draw your attention to good mathematical practice. So you need to bear in mind to always use the correct units, doing unit conversions if you need to, and use appropriate significant figures. In other words, the least sensitive number of sig figs quotient in the question. So don't be surprised if you come across things you haven't heard of before, particularly if you're going to give the paper a go in your first year. Normally the paper is taken around January or February, and therefore if you're doing it in your first year, there'll be lots of stuff you haven't been taught yet. That's actually okay. The paper's more about having a go rather than getting a high score. So the paper is much more about giving it a try, just seeing what you can do. Use a bit of logic and problem solving using the information that you're given. It's not about having to have come across the stuff before and remember it. Okay, so when you get your paper, you'll get this periodic table with it, and if you have a look closely at some of the atomic masses, you'll see that they're quoted to a greater number of decimal places, perhaps compared to the ones you'll find on your exam board's periodic table. So the advice would be to use these values here instead of ones you happen to be recalling. So you might have been coming across sodium or chlorine or carbon, for example, quite often, and now have an idea of what their relative atomic masses are from your previous periodic table you're using. Don't do that, use this one here because the calculation will require it. So this question is in our introductory pack for first year students that are thinking about trying the Chemistry Olympiad paper because it's, like I said earlier, about areas of chemistry that you'll have come across by about November, December of the first year of your course. So just having a look through it, you can see things like dot and cross diagrams, oxidation states, bond angles, all that kind of stuff, and equations as well. So just because it's about accessible topics, don't expect it to be a walk in the park. It's going to be hard, but it's going to be something you can probably get started on. So they start off. So in this case, what happened in 2005 is a massive hurricane, they named it Hurricane Katrina, hit New Orleans. Now, New Orleans is quite a low-lying city, and they have what are called levees to protect them from the ebb and flow of the tide in the Gulf of Mexico. What happened was these levees were broken, and the whole of the city was flooded with a lot of damage, a lot of loss of life. And for the people who were, I wouldn't say lucky, but they did survive, some of the people who survived, there was obviously the need for a clean-up operation because obviously the sewer system would have broken down. And chlorine dioxide is very toxic to microorganisms, so it was used in large quantities to help clean up afterwards. So the first question they ask you to do asks you to draw a dot and cross diagram of a ClO2 molecule only showing the outer shell electrons. And it asks for an estimate of the OClO bond angle. So thinking back to GCSE, you'll know that chlorine has 7 outer shell electrons per atom and oxygen has 6. So therefore, because they're both non-metals, they have to be bonded covalently to each other. So each atom has 8 outer shell electrons, including any shared electrons in the form of bond pairs. So a good idea to start off with is to draw your overlap between the outer shells with lots of room in case a double bond is needed, which in other words will need 2 electron pairs, 4 electrons in total. So the next thing to do is to populate each atom with the number of electrons it has to start with. In other words, 6 for oxygen, 7 for chlorine. Now chlorine is less electronegative than oxygen, so we'll probably have to share more of its electrons than the oxygen atoms do. That generally tends to happen when you get atoms of different amounts of electronegativity that react with each other and bond. The one that has more electronegativity will be less likely to share, and then therefore will force the one with less electronegativity to share more of its atoms. So each oxygen atom shares 2 out of its 6 electrons. So each oxygen atom now needs 2 more electrons to make up its octet. Now something interesting has happened here. You're probably noticing something with the chlorine. Well, 2 things really. First of all, it's left with 3 unbonded electrons, so it has 1 electron on its own. So instead of having a total of 8, the chlorine has 11 electrons in its outer shell. So why has it had to do this? So in order to satisfy the demands of 2 oxygen atoms in terms of electrons, some of the chlorine atoms' orbitals have been rearranged from inner shells into the outer shell, so that there's now the ability for the requisite number of covalent bonds to be made. So this phenomenon is called expansion of the octet. So I've covered expansion of the octet in one of my other clips. So on my channel, if you look at Quick Review, More Challenging Dot Cross Diagrams, you'll find out a little bit more about expansion of the octet. So after that shameless plug, now we can move on to part B. But I've just realised that they've asked us to do an estimate of the OCl-O bond angle. So there's 1 lone pair and 2 bond pairs on the central atom, which would lead you to derive your shape from the linear shape, a little bit like carbon dioxide, for example. But the presence of the lone pair means there's more repulsion. So the lone pair repels the electrons in the 2 Cl double bond O bonds by approximately 2.5 degrees. The unbonded electron will cause a little bit further repulsion. So this gives us approximately 116 degrees if we do it that way. However, it's worth bearing in mind that the repulsive forces might act in slightly different directions to each other. The way I've drawn it, it might seem that they might act in opposite directions to each other. So a little bit of flexibility about the exact angle is allowed here. So let's now move on to part B. So in this question they talk about something called disproportionation. In case you haven't come across this word and you haven't looked it up, basically it means the simultaneous oxidation and reduction of the same element in a redox reaction. So for this to work you need at least 2 atoms of the element concerned, because you can't oxidize and reduce a singular atom at the same time. So for example, if you had 2 different chlorine atoms somewhere in a molecule, one could be oxidized, one could be reduced. So for this one, for part 1, they want the oxidation states of chlorine in each of those compounds. So the first thing to do is to use the oxidation number rules for the 2 elements you can do. So starting with chlorine dioxide, you know that oxygen is -2, so there's 2 of them, so 2 lots of -2 is -4. So because it's a neutral compound with an overall charge of 0, you need +4 to balance that out. So chlorine must have an oxidation state of +4. In the second example, HClO3, 3 lots of -2 gives you -6, add the hydrogen onto that, gives you -5, so the chlorine must be +5 for the same reason. The whole molecule has to be neutral. So applying the same logic on the third example gives you +7. So when you're doing equation balancing, start off by putting in anything that you've been given by the question. So you've been told about all of these compounds. And I've also left space for balancing numbers because I haven't worked them out yet. It's part of the job I'm about to do. So HClO3 going to ClO2 means a decrease in oxidation number, in other words a reduction, of -1 for chlorine. At the same time though, HClO3 turns into HClO4, which means an increase in oxidation number, or oxidation, of +3 for chlorine. So the reduction needs to happen 3 times to support the oxidation once. So you need 3 HClO3s to allow for this, which allows us to deduce the remaining balancing numbers. Okay, let's go on to part 3. So it asks us to give the structure of a molecule of perchloric acid, which is HClO4. Now, as we know, we worked out earlier, the chlorine here has a +7 oxidation state, so it's got to have 7 bonds, which I've now put in. But if we take away the hydrogen to make the ClO4- ion, around the chlorine you have 4 bond pairs and no lone pairs, so it's 109.5 degrees, or tetrahedral. So this part asks for another equation, but they give you some clues to work with. So the sulfur dioxide is one of the reactants. NaClO3 is a reactant, but it's partially reduced, and ClO2 is one of the products. So again, let's put down what we know. I forgot to mention that there's one other product, so let's go back and try to put something together here. So although I've put down what we know already and I've left spaces for balancing numbers, we still need to think about how many moles of each compound we need to use. We also know that there's going to be a sodium-containing product. So all the chlorine atoms appear to have transferred from sodium chlorate to ClO2, so the other product must contain sulfur. So the sodium-containing product I'm going to propose is sodium sulfate. Now if you've got 2 sodiums in sodium sulfate, that means you're going to need 2 moles of NaClO3. So we've now got our balanced equation. So let's go down to the final bit, part D and E. So some more equation work here. Okay, so it gives you ClO2 as a product. So we have CO2 as a product, oxalic acid as a reactant, and NaClO3 as a reactant as well. So it says in the presence of sulfuric acid. So we could consider that to be a reactant this time. So this time you'll see they've given us a little bit less information than we might need. So where does the sodium go, where does the sulfur go? So we can have a think about that based on what we deduced last time. So we could be a little bit canny here and have a look at COOH2. It could break up into 2 CO2s and also 2H+. So it's an acid, if you remember. It was called oxalic acid. So if we now have to think back to the previous part of the question, in part C, we deduced that 2 NaClO3s converts into 2 lots of ClO2. That means we can put a 2 in front of each of them. Now the reason for that was that we produced Na2SO4. So if we now have a think about everything that we've done, there's only one thing left to do. And that's to mop up the remaining H and O atoms by making 2 water molecules. Okay, so let's now go on to part E. So in the first part, they ask us to suggest a formula for sodium chlorate 3. Sodium chlorate 3 means the Cl is in the +3 oxidation state. So sodium is +1, so the chlorate 3 ion must be -1 overall. So to achieve this, for chlorine to be +3, 2 oxygen atoms are needed. So therefore it must be ClO2 minus. So for the first part, the formula is NaCl2O minus. Sorry, NaClO2. So this time, you know you've got sodium chlorate 3 at the beginning, and chlorine. You know you've got ClO2. So what you're going to have to do is think about what other product you could have to get rid of sodium. So it shouldn't be too difficult to work out that you've got NaCl there. Now all you have to do is the balancing. So ClO2 and ClO2 can stay the same either side. There's 2 chlorines in the chlorine gas, which would give us 2 NaCl, and for that to work you'd have to have 2 NaClO2. So now you have 2 ClO2s on the left and 1 on the right, so you can just double up the one on the right. And that's us done. Okay, I hope you found this useful. I hope you also felt that it was accessible and it was kind of associated at least to some of the stuff that you've been studying in your chemistry so far. If you think this gives you a bit of a taste for Chemistry Olympiad, don't forget to go back and have a look at some of the past papers. We also have them on our VLE. But in the meantime, thanks for listening. Until next time, see you soon.